The next discrete distribution we're going to talk about is called the Bernoulli random variable, and this one's very closely related to what we call the binomial random variable. So we're going to cover both of those in the same video. The idea here is we're going to say we have a Bernoulli experiment when we perform some task that has only two outcomes. So those two outcomes can be thought of as either a heads or a tails, a success or a failure, yes or no. Generally we call them success and failure, and you can define the success however you like. And we're going to denote the success as a 1 and the failure as a 0. So if x is equal to 1, it's a success. If it's equal to 0, then it's a failure. And so we can talk about the probability of success and failure in terms of pi. So pi is a Greek letter, so that shouts parameter. And so we say pi is the probability of success, which means 1 minus pi is the probability of failure. Sometimes the convention is taken that the success is defined such that pi is less than 0.5 for convenience. That's not always going to be the case, but I guess we'll go with that for now. But notice that the probability of 0 plus the probability of 1 is equal to 1, and pi has to be between 0 and 1 to follow all the conventions for probability. So what's the mean? The mean value is pi, and the variance is pi times 1 minus pi. So how would you get that mean value? Expected value of x is going to be the summation of x times p of x. So that's going to be x is 1 times pi plus 0 times 1 minus pi, and that's pi. And you can do the same thing to find the variance. I'm not going to work through that though. If you're curious, you can. So the standard deviation then is the square root of pi times 1 minus pi. And so this is actually going to be the basis for what we call a binomial random variable, or the binomial distribution, where we're going to take independent Bernoulli trials and count the number of successes. So in other words, we're going to take Bernoulli experiments, we're going to repeat it n times, and then we're going to count how many successes we have, assuming that the probability remains constant and each trial is independent of each other. Then x is written as the number of successes out of the n trials. So we'd say x is equal to the summation of x1, x2, and so forth, where each of these x's over here are simple Bernoulli trials. So they either result in a 0 or a 1. And if we know what n and pi are, then we know everything we need to know about this distribution. In other words, the probability that x is equal to some number between 0 and n can be completely determined by n, pi, and the number that we're interested in. So here are the characteristics. There are two parameters, n the number of trials, pi the probability of success, and the PDF is just the probability that x is equal to x. Now we're going to actually write it out as a function of x. So what we have is n factorial divided by x factorial divided by n minus x factorial. That's just, remember, n choose x. So n factorial over x factorial n minus x factorial. Go back to chapter 5 and look at the counting section if that doesn't ring a bell to you. We did talk about that last week. Then we're going to multiply that by pi to the x power as 1 minus pi to the n minus x power. So what this is saying is we have x pi's, so we have x successes, and the probability of each of those is pi. So if I've got x successes, then I have pi multiplied by itself x times. But then I also have n minus x failures. And so the probability of each failure is 1 minus pi, so I multiply those together and I get 1 minus pi to the n minus x. So this constant out in front here basically says how many ways can I rearrange x successes and n minus x failures. And so if I want to use Excel to find the probability density function, I can use this function here, binom.dist, put in x, n, and pi, and then here's the important part. The 0 tells me that I'm using the PDF. And if I want to use the CDF, everything's the same except for that last argument is a 1 instead of a 0. So we're not going to write down what the CDF is because it's just the summation of the PDF, and there's not a nice form, which means this function here should be your best friend if you ever have to deal with a binomial random variable. In fact, if you have a function like this available to you, then you don't need to use tables or charts, although there are some in the textbook. Just use the binomial.dist function and you'll get back exactly the probability that you're looking for. So what are the values that can be put into this function? We have x, which is anything 0, 1, 2, 3, all the way up to n, and pi has to be between 0 and 1, we already mentioned that, and n of course has to be bigger than 0. So a good example of this, or one that's easy to think of, is shooting free throws. If you like basketball, you know about free throws. You stand at the line and nobody's in your face, nobody's going to foul you, and you just shoot, and you count how many you make. So you're going to shoot 10 free throws. If you on average make 70% of your free throws, then you would say pi is equal to 0.7. And if you're going to shoot 10 of those, how many would you expect to make? Well, that's the mean, n times pi. And that makes perfect sense. If I shoot 10 and I shoot 70%, I would expect to make 7 out of the 10. So to get the standard deviation, we're going to take the square root of n times pi times 1 minus pi, and that's something that we're going to need to know about. If you want to make randomly select these things, you can, although we're not going to really do that, so I'm not sure why I even put that in this on this slide. But what happens if pi is equal to 0.5? You get a symmetric distribution, and if you have something different than 0.5, then you're going to have a skewed distribution, and the skew is going to be the opposite direction of what pi is. So if pi is less than 50%, you're going to have right skewed. If it's greater than 50%, you're going to have left skewed. So let's look at an example or two or three. The first one is quick oil change shop, and what we're going to do here is imagine you've got a mechanic shop that changes people's oils, and they don't like to have their customers show up and say, where's my car, where's my car, where's my car? So they're going to say that if that happens, it's considered to be late, and they don't want that to happen. But the service time is going to be defined as whether they're late or not. So we have two possible outcomes, either late or not late, and in a given day there are going to be X cars that are serviced. Sorry, of the cars that are serviced, X is going to be the number that are late out of the total. So we're saying late is a success, although you might call that a failure in real life. And so the assumptions we have here are that the cars are independent of each other. That's maybe not the best assumption here, because if you have one car that has to go after another car, and the first car is late and it takes longer than usual, maybe a bolt gets stripped, or they don't have the right oil, or who knows what happens, probably that's going to affect every other car that comes in there. So this is an assumption we're making, although maybe it's not the best assumption, but we're going to say the probability of the car being late is also consistent, or rather it doesn't change. So we could ask the question, what's the probability that exactly 2 of the next 12 cars serviced are late? So n is equal to 2, and we need to know what the probability of a late car is, and it turns out they're telling us it's 10%. And so we could say, what's the probability a car is not late? It's 90%. And then we can plug in this formula, p of x is equal to, and choose x times pi to the x times 1 minus pi to the n minus x. So it's now just a simple matter of plugging in n goes here, x is here, pi goes here, and 1 minus pi goes here, plus the other parameters as needed. And so here's what we get: 12 factorial over 2 factorial over 10 factorial times 0.1 squared times 0.9 to the 10th power turns out to be 23%. If we come over here to Excel, we can find that same number by taking, let's say we're going to put in binom.dist s. Number s is the number of successes, so we're going to say it's 2. Number of trials is 12. Probability of success is 0.1. And we want not cumulative, so this is this PDF we're looking for. So we're going to put a 0 in there. And we get the same number, 0.23128. That's 0.230128, I should say. Same thing as what we had over here. Okay, let's look at another example. On average, 20% of emergency room patients at Greenwood General Hospital lack health insurance. So we take a random sample of 4 patients, and we want to know what the probability that at least 2 of them will be uninsured. So in this example, we're going to be using the cumulative distribution function, and we want to know x is the number of uninsured patients. That's what we're going to define as a success, and the probability of success is 0.2, which means the probability of insured is 0.8, and n is equal to 4. So the possible values that x can take on are 0, 1, 2, 3, or 4. And so we're going to just add the probabilities of each of the numbers in the event that we're interested in. And so in this example, we want to know the probability that at least 2 patients are uninsured. And so what does it mean by at least? That means 2 or greater. So we're looking for the probability that x is equal to 2 plus probability that x is equal to 3 plus probability that x is equal to 4. That turns out to be 18%. So if we come over here to Excel, we can figure out that probability by saying 2, 3, 4, and then we're going to say this is equal to binom.dist 2, comma, now we're doing 4 trials, probability of success is 0.2, and we're not doing cumulative, so we're going to take that and just copy it, and then we want the sum of those things, and we get 18.08%. Now another way to do this would be to use the cumulative distribution, and the cumulative, well, we'll get to that in just a second actually, don't let me not get ahead of ourselves. So we could say, what's the probability that we have fewer than 2 patients with insurance? And in this case, we need to be careful what we mean by fewer than. In other words, what's the inequality we're looking for? And it turns out that it's x is less than 2. That turns out to be the same thing as probability x is less than or equal to 1. And we can write that down, p of 0 plus p of 1. Let me move that. And we can ask other questions like, what's the probability that no more than 2 patients have insurance? So what we need to make sure we know is what the inequality no more than means. In this case, it's less than or equal to 2. So not more than 2 means less than or equal to 2. And so we can plug all these numbers in to get the values that we're interested in. But what I want to show you back over here is if we want, say, the probability that x is less than 2, which remember is the probability that x is less than or equal to 1, we can get that by taking binom.dist 1, 4, 0.2, and now we want a cumulative value instead of non-cumulative, so we're going to put a 1 in right there, and we say enter, and there we get 0.8192, which is the probability, the cumulative probability of being less than or equal to 1. Now notice if I take 1 minus that, what do I get? I get exactly the same thing as what I had up here. So this was much easier to calculate, wasn't it? I just said binom dist one time and put in a 1 there instead of zeros. Over here I had to calculate it 3 times and then sum them up. So if I can use the cumulative distribution function, that's going to be my the easiest way to calculate these things. So if I want to know the probability x is less than or equal to 2, what am I going to do? I'm going to come over here and say px is less than or equal to 2, and this is going to be equal to binom.dist 2, 4, 0.2, 1, and there I have the 97.28%. So the mean, if I have 4 samples, I should expect 0.8 patients on average, and standard deviation is also 0.8 patients in this case. So whenever I'm dealing with discrete random variables, not just the binomial, but any discrete, I need to make sure I know what I mean when I say at least 2, no fewer than 2, or more than 2, and sometimes it's helpful to actually write these things out. So I've got 0, 1, 2, 3, 4. Those are all the possibilities. So at least 2 means 2 or more. So I can mark that and say here. Fewer than 2 says, down that way. So the point I'm trying to make here is that the endpoint is important when it comes to a discrete random variable. And in other words, probability that x is less than or equal to 2 is not the same thing as the probability that x is less than 2. So I've got to be a little bit careful about that. So here's one more example. You decide to hire a monkey to take your multiple choice statistics quiz for you. There are 10 questions and 5 answers to choose from for each question. What's the probability that you get at least 50% on the quiz? Okay, so what does it mean to get at least 50%? That's the first question we want. Well, the first thing we want to do is say x is the number of questions that you get correct, and we're going to say that's binomial, and there are 10 questions, so n is equal to 10. So this is notation you'll see from time to time. N is equal to 10, and pi is equal to what? Well, if there's 5 answers to choose from for each question, and assuming the monkey's going to randomly select, that means pi is going to be 0.2. So in order to get at least 50% on the test, what does that mean? That means x has to be greater than or equal to 5. So we have the probability x is greater than or equal to 5, which is equal to 1 minus the probability x is less than or equal to 4. So why would I do it this way? Use the law of complements, because I can use the CDF function on this part to get what I'm looking for. So if I come back over here to Excel and I say this is the monkey quiz example, I will say I got 1 minus binom.dist, number of trials is 4, number of successes is 4, number of trials is 10, probability of success is 0.2, and cumulative is true. So I get So chances are pretty bad that I'm going to get a good score on the test if the monkey is randomly guessing. So that's all I've got for this video. We went over the binomial distribution, talked about probability density function and cumulative distribution function. We looked at 3 examples, and a lot of the stuff what we did here is applicable to the other random variables that we're going to talk about in the next few videos. So we'll see you in the next video. Send me an email if you have questions.